Okay, so now what we're going to talk about is this the Blackwell PVT and both for the gas phase and the oil phase, the complete Blackwell PVT table that would be needed, for example, to do reservoir simulation or to do Prosper calculations using Blackwell formulation. And you would not want to use, for example, the correlations given in the Prosper software. You don't want to use correlations for these gas condensate systems. They don't really apply. So you'd need to generate the Blackwell tables in equation of state-based PVT software. As noted here, basically the issues related to Blackwell PVT table generation for gas condensates. This is really a pretty general treatment, but so we're going to need to use an equation of state to generate the Blackwell table. You'll need to first have a composition that you want to use. So it could be an average composition of the reservoir. It could be typically we'll use the composition of the fluid in the reservoir that has the highest saturation pressure, highest dew point pressure. So that might be near the bottom of the reservoir if there's some variation with depth. But you need to pick a composition, and you need a temperature. Each Blackwell table will be at a specific temperature. You'll have to define the surface process, because all these Blackwell PVT properties will depend on the surface processing. You know, everywhere from the worst process, single stage flash, you'd probably never use, to in the case here, just for that goof paper, there's a 3-stage separation process being used. I don't remember whether this was something that was optimized or picked random. I can't remember where these numbers came from, but the pressure and temperature of each stage needs to be specified. So we did talk about that having an impact on the PVT properties. And what I'll make a footnote here is that the calculated CGR, which is referred to as solution UR, is increasingly dependent on the separator process. The leaner the condensate. So if you've got a 300 barrel per million condensate, you can put in a lot of different 3-stage separators without it having a big effect on it being 300 barrels per million or 320 barrels per million or 275 barrels per million, something like that. But if you go to a lean condensate and you change those separator conditions around, you might have a 40 barrel per million or a 20 barrel per million, or maybe a 52 barrel per million. So it can have a much bigger impact on the CGR, is more dependent on this process for leaner condensates. So the HISIS group, the process engineering group, is going to really have to be much more diligent, much more optimization of the surface processing facilities, the leaner the condensate system. And again, the reason for that is what we talked about yesterday. That first stage separation, you have a lot of gas. The leaner it is, the more gas molecules you have to absorb the heavy components into that gas, and the less efficient it becomes. So that's the reason for this. You have a lot more gas molecules to absorb heavy components away from the liquid products, which you like to have. So it's requiring, it's more dependent on these conditions. Then you got the depletion process. You have to choose some kind of a depletion process to go from the initial saturation pressure down to lower saturation pressures to cover the entire range of the PT diagram, the entire range of two-phase conditions. We typically use a constant composition expansion. We may use a constant volume depletion. These will typically give very similar results. very similar black oil PVT tables. The exception to this, which is discussed in the original Favong-Whitson paper for gas condensate specifically, is that the oil viscosity that affects the blockage region 1 pressure drop, the oil viscosity coming from the CCE test is more appropriate than the CVD oil viscosities. Okay, now it's discussed why and everything there, but it's just a footnote you need to make that for gas condensates, the CCE actually, for that one specific reason, because the little RS, the BGD, will be very similar for these two, but the oil properties can be enough different, and it's the CCE oil viscosities that actually are more appropriate to use to treat this region 1 pressure drop. So basically, the CCE oil viscosities are better. I'll just make a footnote there. And if you want to look at why and the magnitude of that, in fact, I'll show you from that paper. This is from that paper. Let's go to the end. Being very cooperative.
When it's in the full screen mode? Is it only when the full screen mode or?
No.
Wait, is your keyboard working? Did you check before?
Yeah.
It's working. Okay. So it is scrolling, but not.
Yeah. Okay.
Can try to use this. Those.
Well, this is in.
Yeah.
Okay.
Those were.
Okay. Let's see here. See if I can get. Should be in here somewhere. There it is. Okay. So these, this doesn't actually show, but this is when it says default, that's from the CVD. Okay. And then if you actually take the oil viscosities in region 1, near the wellbore, as a function of time and at different pressures, you can see these are taken from the compositional simulator. And what basically this dashed line is essentially the CCE type oil viscosity. The CCE oil viscosities of the original gas will be lower than the CVD viscosities. That's basically, this talks about that. And you can see it's more appropriate, particularly down in this region that's of interest for the condensate block, which is at the lower pressure range. So that's now any Blackwell table being created will be created into two tables actually. Table 1 is the saturated properties and table 2 is the undersaturated properties. So we'll look at an example table here in a minute, but basically these are saturated oil and saturated gas properties in the first table, and then those saturated oil and saturated gas compositions are taken to undersaturated pressures to get the undersaturated table. So we'll look at that here in a second. But if we just first look at the properties themselves that make up a Blackwell PVT table, for the gas phase, it's the solution oil gas ratios, solution CGR, little rs. It's this BGD that takes into account the fact that the BG is a ratio of reservoir gas volume to the actual surface product gas volume, and then the gas phase viscosity. For the oil phase, we have solution gas oil ratio for this oil here is actually what we usually refer to as retrograde or reservoir condensate. And it has the solution gas oil ratio, the formation volume factor, and its viscosity. And then we have to calculate the phase densities, which for most gas condensate fields don't make any difference. You don't have much gravity segregation, if any, ever in a gas condensate reservoir. So gravity within the reservoir is a non-issue for gas condensates. You don't get gravity segregation. Because why? Because the oil mobility is so low. Okay? That's why. So it has zero mobility, so it doesn't move anyway with or with gravity forces or anything. So you don't have gravity segregation. You don't really need densities per se for gas condensates. But if these Blackwell tables are being used in your building your tubing tables, then the gas and oil densities start becoming important. Okay, and the gas density, of course, all of these are a function of pressure at the particular temperature of the table. These are a function of pressure and temperature. So to get the density as a function of temperature, we have to have two numbers that follow the entire each Blackwell table has a single set of surface oil densities. And the only purpose of these surface oil densities is to calculate the reservoir gas density and the reservoir oil density. That's the only purpose of those. So when in like Eclipse 100, I think the command for this is surface. The keyword? I'm not sure. Remember? Nobody remember. Maybe seeing the other remote. But basically, there's some command to put in the densities, the surface oil densities. I don't know if it's surface or not, but they have to be. Does anybody out there know?
Density keyword.
What is it?
Density.
Okay. All right. That makes sense. Okay. Density. Okay. And how this is used, these two numbers go into calculating both the reservoir gas density and the reservoir oil density. And the equation for this is rho, make it in red, Y. So it's rho G, that's the surface gas density, plus rho surface oil density times little rs, which is a function of pressure, over BGD. Okay? So that's the equation to get the reservoir density or the density at P and T. And then for the oil phase, the equation is surface oil density plus surface gas density times solution gas oil ratio, all divided by BO. So internally in Eclipse or internally in Prosper, it will make these calculations of gas and oil density at P and T. You don't read those in as tables. You just simply read in these two numbers here together with the other pressure dependent properties.
One question.
Yeah?
You said we don't have gravity segregation in the reservoir as the oil mobility, condensate mobility is low. How's the situation in the hydraulic fracture due to the high permeability?
Yeah, so the question is, if you're modeling like a well with a hydraulic fracture or many hydraulic fractures, then in those hydraulic fractures, if the model actually grids up the hydraulic fracture, then yes, you would expect there to be some gravity segregation in the hydraulic fracture because of its high permeability, but probably it would only be segregating if the well's shut in or at low enough rates, I'm guessing. I suspect that the pressure difference between the upper part of the hydraulic fracture and the lower part of the hydraulic fracture would be very small because of the high conductivity. So you wouldn't have, I mean, you might get some gravity segregation during flow, but I would not suspect very much. Again, why speculate if you can calculate? But you're right. If there's going to be any gravity segregation in a gas condensate well, it would be in like a hydraulic fracture. Or if you have a naturally fractured reservoir and you have like a dual porosity treatment, then again, the gravity segregation in the natural fractures, part of the dual porosity, could see gravity segregation. That's true. So yeah, the exceptions for having gravity segregation in the reservoir, they are there. There's exceptions to every rule, and the hydraulic fracture, natural fracture would be good examples of that.
Okay, thank you.
Yeah.
A question why I asked is because when we did the explicit hydraulic fracture modeling, including the gridding,
Right.
we really saw like a condensate swamp, like highly saturated bottom part of the fracture with condensate, where it then also has mobility and then can flow into the well.
Right.
And our question was always whether this is realistic or some modeling artifact.
Yeah, no, I mean, if you saw it also during the flow period, then, the equations would be segregating, they segregate. What I would have done to test if it has an impact is that I would turn, I would try to turn off the vertical segregation in the hydraulic fracture artificially for one run, and then see if it has any impact on the well performance. Yeah, that's, I mean, just to see whether that segregation in the hydraulic fracture has a bottom line impact on the well performance. My gut feeling is it would not, but there's only one way to try, and that's what I'd try to do is turn off the segregation without turning off full communication, but just see if it has any impact.
Good morning. Okay, thank you.
Okay.
I also have a question.
Yeah.
For the correct experiment to make the black oil table, you mentioned that for viscosity it's better to use the CCE. It gives a more realistic properties viscosity table. But for the other properties like RS or CGR, shouldn't we use the CVD because that's the process that simulates the depletion? And some softwares, if I want to name it like PVTP, they use CCE to generate the black oil table. Is it correct?
Yeah. So for the gas properties, little RS, BGD, and gas viscosity, I don't think you'll see any real effect doing a CCE or a CVD. I'm almost for sure. Okay. For the oil properties, you will. Now, it's the gas properties that are most important. So yeah, it doesn't really matter. And I think we normally use the CCE ourselves for gas condensates because mainly of the oil viscosity issue. But you can always run you can if you use PVTP, apparently. If they don't let you use CCE or CVD, then you won't be able to check it. But if you use another software that allows you to run CCE or CVD, you'll probably find the gas properties don't change very much at all.
I think most PVT software use Witzentorp method, which is based on CVD.
Well, no,
So,
A few, but maybe not.
yeah, I don't know.
Yeah, the Witzentorp method is kind of it's using CVD. It's talking about gas condensate, and it wasn't aware. It doesn't talk about the viscosity problem there. That's true. But basically, the depletion process, the recommendation is CCE if you're going to have to pick one. So your problem would be is that if your software only allows you to use the CVD, that could be a problem. Then you're going to have to take care of the oil viscosities manually. Because what this paper shows is that if you use the CVD type, the solid lines versus the CCE dashed lines, then the actual performance rate time performance, the condensate blockage, you see it's almost a factor of 2. It's down here. It's 0.2 versus 0.3, so that's 50% higher viscosities. So you'll have a higher blockage effect using the CVD viscosities. Okay, and I think that's shown. Black oil versus compositional, probably here. Yeah, here you can see black oil with the standard versus, so you can see that what kind of effect it has. So the compositional run, which is, let's call it the correct answer, is the symbols. The black is using a CVD table depletion process, and the dashed line is more like the CCE. So that's the magnitude of impact it has. It's not like a huge impact, but it's like, why not try to get it better using the CC? And so basically for the gas properties, what I'm gonna guess is that these are gonna be all of these properties. If you CVD is going to give you the same properties as the CC. Now, when it comes to the RS and BO, the only thing the RS and BO do are give you the liquid dropout curve, and we don't care about that. We've already talked about that. So if the RS and BO, we have to put in some strange RSBO curves to get Eclipse 100 to run because they're non-monotonic. It'll give you liquid dropout curves that are not really quote unquote correct, but it's not going to affect anything. And you'd see that if you ran compositional versus black oil. You'd see that you wouldn't see a real impact there. So it's not a first order type effect.
But if condensate blockade is an issue, then you will see the difference, right?
Not in the BO, no, because the liquid dropout in the condensate blockage region, it's a CCE liquid dropout at low pressures. So it's a VO over V total. So your VO is going to be off a little bit, but where you're changing the properties of the is probably mainly at the high level. So you can so you really wouldn't expect the blockage effect to be altered by these if you have to use artificial BORS that are monotonic. Okay. And Singh, who's I think with us here remotely, if he's had different experience, if anybody's had experience with that not being the case, then mention it. But I don't think so. I don't think this is going to be a problem. The viscosity is a more direct thing, and it's the largest differences at these low pressures. So yeah. So I think in general the CCE for gas condensates is a good rule of thumb. Okay.
Sorry, but then why, when we have a CCE experiment in the lab and CVD, we have different CGR from the test? So they are really, really different, but they are different. So if I use the CCE, then actually I'm not really considering what's happening in the reservoir. So I don't get the CGR that I see in the CVD test.
Well, that I haven't seen. I mean, that's.
But how do you get CGR from the CCE test?
Yeah, I mean, if you generate the Blackwell tables with the CCE and with the CVD, and if you're saying this is not what you find, that the little RS is different for CVD and CCE, I haven't seen that before. The liquid dropout may look different, but the equilibrium compositions as a function of pressure should look very similar, whether it's CCE or CVD. Okay, basically it's what you're looking for is this equilibrium how does this composition change with pressure? And we could, you know, it would take a little bit of time to create a Blackwell table. Maybe we can do that and show you after lunch. Is it a lean or a rich condensate you're seeing this difference between a Blackwell table from CCE and CVD? I didn't catch who was commenting on this.
Shaho.
Yeah. Is it a rich or a leaner condensate?
Well, you know, my comparison is between different PVT package because I have PVTI, I use PVTP, and I see they are creating different PVT tables.
Okay, so
and the difference is PVTI uses CVD, and that's the only option that you have there. And PVTB uses CCE, and that's the only option that you have there. So that's
okay.
Maybe you are right.
But yeah, that's
this is
interesting.
Something different. But it is lean. It's not that rich. The gas condensate that I'm. Yeah.
Okay, so we can redo this COOF example, and I'll do it with. I think in sensor we can actually run with CVD or CC. Is that right or not?
No,
Is it only CC? No, maybe it's only CVD. Okay. Yeah, we'll look at this and come back to it. But what I would say is that if you're using two different packages, PVTI and PVTP,
but what
they should have exactly identical properties at the dew point for the CCE and the CVD. So if you're not getting exactly the same properties from PVTI and PVTP at the dew point, at the initial dew point, then there's something else different going on in the two packages. Because they have to be identical at the dew point because there's been no depletion, right? But the problem is that there's so many ways to get an EOS loaded into PVTI and another EOS loaded into PVTP. They might use, you know, there could be other reasons for the discrepancy. So I would make sure that the two tables have identical properties, both gas and oil, at the initial saturation pressure. And if you say that, and then you say that the little RS curves differ, then I'm interested. Then I need to
Then how much does it differ? Like, I don't know. Is it?
Yeah, I mean,
how significant is the difference? Also, Shaho, can you explain what you're
saying?
Yeah.
To be honest, in PVTV, there is also another thing. When I do, for example, a separator test, I get something different that what I get from the PVTI.
Yeah. So what you're seeing is what I suspect is that there's other stuff going on that you don't have a completely consistent.
Exactly, because still you need to still consider the introduce a separator to create your Blackwell table.
Yeah.
But still, even if I do a separator test, get different GOR or CGR with the two different packages. Yeah.
So there's something else other than CCE versus CVD there is a problem.
Could be other factors, affecting.
Yeah. And so basically, what I'm saying is that you should get exactly the same set of properties: RS, BO, MUO, little RS, BGD, MUG, exactly the same 6 properties at the initial saturation pressure for the 2 PVT programs. When you get that, if you can get that, then I don't think when you do CCE versus CVD, you'll see much difference in anything but the oil viscosity.
Yeah, we have actually a Whitson monthly article about that, the one that Bilal wrote, where he talks about the consistency when you transfer in an EOS from one package to another. So I sent it in the chat of the WebEx, so everyone can.
Yeah. So the problem is that it's one of these engineering tasks that nobody likes to do. There's so many ways you can get a little bit of difference, and because the software packages have different defaults, and maybe the defaults override what you actually tried to read in. It can be a process that takes a day or two to kind of verify that you're getting exactly the same results from the 2 PVT packages. And who takes those 2 days? It's essentially nobody. But this link, this monthly article that Bilal here, sitting here, wrote is specifically to talk about how important that is, because there's so many ways to get it wrong, moving an EOS from one software application to another. So, okay.
Yeah, usually when I do that, so I create the EOS in both packages and then export compositional model, and then compare the keywords and the properties. If they are the same, then I know that my equation of state has been set up similarly in both packages. So
that makes sense, like an Eclipse 300 file or something.
Yeah, exactly.
Yeah, that's a good way to do a check. I think still, if you've done that and you still see these differences in like a separator test from the two packages, there's something else you haven't found yet. There's, I don't know what it is, but if you have those two dumps of the EOS from the two packages giving the same Eclipse 300 input file, then you should be able to do a separator test in PVTI and PVTP and get exactly the same GOR, CGR, API gravity, everything. So I'm still not sure. Yeah. Okay. So if we just look real quick at the example from this CUF paper, again, I don't want you to be able to, you don't have to follow it, but basically I'm going into this paper directory, I'm going to the tables, and in this first table 1 to 6, there's this output file from the Blackwell run, input file from the Blackwell run, and that's what I'm going to open up here just to look at an example Blackwell tables. There's two Blackwell tables in this file. The one is for this K1, K4 formation, and the other for the K2, K3, which has a higher H2S content and a lower methane. So these are, so let's just look at these tables. Here you've got the surface density I was talking about. That's this surface oil density. Here's the surface gas density. They have to be given. Here's the saturated data, the table, saturated table, very clearly marked. And in the saturated table, you'll have pressures, which are the saturation pressure. So for the oil properties, those saturation pressures are bubble points, right? So this pressure column are bubble points corresponding to the BOB, RSB, and viscosity B. Okay, and so the initial oil, which is in this case the incipient oil from the dew point calculation, has this BO at 5100, 1.54. As you lower in 1087 GOR, solution GOR, and at 0.415 viscosity. When you lower the pressure, normally you would expect the saturated BO to decrease, the RS to decrease, and the oil viscosity to increase, right? Because gas is coming out of solution. The reason it doesn't do that is because if you looked at the heavy ends, the C7 plus of the incipient oil, that the heavy ends would be heavier than the oil that is condensed out at 4,000 psi. It's literally a heavier C7 plus, or the stock tank oil is heavier at 5133. So I don't know what the API of this oil would be, but it might be 32 degrees API, whereas the API at 4,000 might be 39. So in the saturated table, you'll have pressure, which is bubble point associated with the three oil properties, and then you'll have the pressures for the gas properties, which are over here. Those will be the dew points of these gases. So the initial gas has a solution GOR of 31, a solution CGR of 31 barrels per million. This is the BG at the dew point, initial dew point, and its gas viscosity. And then as you go to lower pressures, the little RS, see, it's becoming a leaner gas because you're getting condensation, right? So when you condense out, you lose some of the barrels in the reservoir. And what's left for the gas to carry to the surface is a lower CGR. Correspondingly, that will affect the BG, because this BG here is not written that way, but it's actually the BGD. So the BGD has the Z factor, but it also has the, you remember this little RS term. So the composition of the gas is changing, and accordingly, the BG changes because the composition is changing, that little RS term changes, and the Z factor changes. So again, these are, and what you can see is that the CGR doesn't change much from initial down to lower pressure. It goes from 31 down to 11. Okay, whereas a rich condensate might go from 300 barrels per million down to 20. From initial dew point down to lower pressure. And the fact that the little RS doesn't change very much is why the recovery factor of condensate is much closer to the recovery factor of gas for this kind of lean condensate. Okay, we'll come back to that a little bit later. So this is the example of the saturated Blackwell table. You got compressibilities. These are undersaturated compressibility and viscosity. They're not printed here because it's generated from the equation of state. And then the IFT here, that's used in sensor. It's used to, if you turn on the dependence of relative permeability on IFT, there's an option for that. Then you can adjust the relative permeabilities according to the IFT. So for the undersaturated properties, basically what's going on here is that you take that oil, well, the saturated oil that you end up at 500 psi bubble point with these properties here. If you take that depleted oil here and you take that oil to higher pressures, okay, these are undersaturated pressures. So the bubble point of the oil is 500 pounds. It's the identifier of the oil. This BO should be the same as the saturated BO, 1.1391. So this first here is saturated properties. And then for that same oil, not changing composition, not changing RS is not changing here. The properties of oil are changing undersaturated. And likewise, the gas that has a dew point of 500 psi has this BGD and this viscosity and some little RS, what is it, 12.5768. All of these properties here, now these are all not entered. Okay, this is I have to explain why they're not given there. Yeah, it's a little bit complicated. But if we go up to the initial gas and oil here at the dew point, the initial dew point. So basically here we've got the initial saturated gas. This is the incipient oil, BO, and viscosity. This is the initial gas, saturated gas, BG, and viscosity. But if you take that initial gas to undersaturated conditions, then you get undersaturated gas properties as necessary. So you can initialize the reservoir up to 6,500 psi. Okay, you couldn't run this model with an initial pressure of 8,000 psi because it wouldn't have the properties for the gas. Okay, so those are just examples of the Blackwell tables. You have a saturated table and an undersaturated table. Are there questions? It's a little bit confusing because, you know, the different simulators have different formats. The sensor format's different than the Eclipse 100 format, so you have to be a little bit careful in trying to understand them, okay? Are there any questions about using Blackwell properties?
Do you recommend table extrapolation by the simulator, or?
Absolutely not. Absolutely not.
Okay.
Sensor doesn't extrapolate. I'm not sure. Singh, you have to answer that question. I think it's a very dangerous thing to do.
Sensor.
I think to do automatic extrapolation of a Blackwell table. Eclipse 100, I think, does do extrapolation, but I just would be very careful about using that.
Because you can extrapolate in sensor if you ask for the extrapolation. But what Kurt is talking about is if you input a Blackwell table, let's say you input a Blackwell
like
table
this one, we stop at 60,
and then you go with the pressure higher. I actually don't know if it extrapolates. I think it doesn't.
So I think if we try to run this data set, we'll just change this this data set here, and we'll just change the initial pressure just to see. I don't think it.
Apparently it does, because it says for Blackwell problems, be sure to include undersaturated PVT data up to a maximum pressure that exceeds the run maximum pressure that will be encountered during fracturing. Extrapolation may otherwise lead to erroneous behavior in the fracturing period. So it apparently would extrapolate, but it advises you against using that.
Okay, so if we just put initial pressure here to 10,000, I think it's is comment and sensor that. So if we just put both of these layers, right, save that. ERI 10,000. Okay.
Is it the first or the second one? You have two sensors there at the top.
Oh, these, huh?
At the top you have two sensors around piping.
No, this is the.
Is that or the one on the left?
Let's try that. Okay, these are maybe not complete data sets, I think. Yeah, I think. Yeah. Okay. I'll try to do this later, but I'm not sure why it's not running it. Okay, but yeah, I mean, I don't generally recommend it because, yeah, it's because the thing is that if you're generating from the equation of state to begin with, when you do that, you can give a maximum pressure for which it to use the equation of state out to. And I would much rather extrapolate with the equation of state, at least undersaturated properties. Were you talking about extrapolating saturated properties or undersaturated properties?
Undersaturated properties.
Yeah, so
undersaturated properties.
Yeah, so in that case, we'll just classify this into one undersaturated. just ask the equation of state to create the tables to do this. For extrapolating saturated tables, you also have to ask, much rather ask the EOS to do this, but you have to say, but you have to tell how. But you have to tell how. And there's a number of ways to do that. And there's a paper, I think Singh and Favong and myself there's a paper that discusses this.
109596.
SPE
109596.
That's a consistent view.
That basically kind of says different ways to do it. Okay. So now, not all the PVT packages will easily let you do the extrapolation, okay, of the saturated properties. So yeah, it's a big topic. So I'll just kind of direct you there. But you basically you have to use the incipient phase is added to the starting composition that you use. That's one way. You can do you can just recombine it, recombine separator, samples at increasing GORs for example, to a critical point. It's another way. You can use an injection gas being added. This would typically be to your black oil if this is an oil. So if you're doing EOR type studies, you could extrapolate using the injection gas for a gas EOR project added to higher PSAT values, maybe out to a critical point. You can use, that paper also talks about using a compositional gradient. To extrapolate. I think these are all of the methods that are discussed. So
the paper also discusses like if you don't have any EOS and you have black hole tables, you can also extrapolate them. Right? Is it the same paper or different?
Actually, I think there's two papers. I think the one is
there's the guidelines.
EOS versus black oil. I think there's two.
Yeah, the one you have there is the second one is SP 63087.
63087.
That's the EOS versus composition, right? The black oil versus composition.
Yeah.
A question about compositional gradients. In a undersaturated reservoir, do we see compositional gradient vertically, or this only happens if you are below dew point?
Yeah. So when it comes to compositional gradients, just this is really kind of a topic for Friday, but I'll just make a quick comment here. I'd start by looking at this paper, just to get general about compositional gradients. But what that paper clearly shows is that any reservoir will if you use this chemical Gibbs chemical energy gravity equilibrium theory, okay, if you use that, which is what most PVT simulators use to calculate this gradient, if you use something like this, either isothermal or non-isothermal, doesn't really matter. So all reservoirs will show some variation of reservoir composition with depth. Okay? You'll have more methane at the top, less methane at the bottom. So that's for sure. Now, the variation in that composition with depth will be less for highly undersaturated reservoirs than near saturated, okay? Saturated or near saturated. So if everything else is the same and you just change the initial pressure, you start with the composition, you're going to calculate up and down, and you just give it an initial pressure and you give a very high initial pressure, then that gradient calculation will give you much less variation than if you put the initial pressure at that composition equal to the saturation pressure. That'll give you a maximum variation. So I think you're referring to the degree of undersaturation, or at least if it's undersaturated. So if it's undersaturated, yes, it'll always have variation, but the more undersaturated it is, the less variation.
But if I'm not mistaken, for example, in PVTI, if your hydrostatic pressure doesn't cross, so the hydrostatic pressure changes with depth doesn't cross the dew point, it will not create a compositional gradient model for you.
No, it will. It should. We have to use another package. It may not flip from being gas to oil, if that's what you're talking about, calculating a gas-oil contact.
Well, exactly. If you don't have a gas-oil contact, it doesn't create compositional gradient model for you. So it doesn't provide you the composition variation with depth.
That's very strange. I would talk with Schlumberger about that. It shouldn't do that. I mean, it should give you the variation with depth only within the gas, even if it doesn't find a gas-oil contact.
No, but I think he said initially that if you don't have a pressure gradient at all, if you have two depths where you don't include pressure gradient at all, then you will not get a compositional gradient. That's what he's saying in the package.
No, so in any package, you basically have to provide, you have to give them, to make a gradient calculation, you have to give a reference pressure, a reference depth, a reference temperature, and a reference composition at this depth. Okay? That's all you give. And with that, it will give you reservoir pressure with depth and composition. It's a function of depth. It must, whether it finds a contact or not. So you always have to give this information for a gradient calculation. And once you give that, then it should just, you know, whether it's single phase or transitions from gas to oil, doesn't matter, shouldn't matter. So maybe there's another PVTI option to ask for this without the contact. I don't know, but it definitely can do the calculation with or without contact. So I'm not sure. And the point is that this will also give you saturation pressure with depth. So so if you have a gas sample, the reservoir pressure might look like that, and then maybe it hits a oil. So this is the reservoir pressure. So this might be our reference depth. So this is our reference pressure. So we've got a dew point that, let's say, is here from the reference composition. And what this calculation will do is that it'll calculate, you know, I'm not going to plot all the compositions, you know, the ZRI, you could plot for each component. But when you get the composition, you can calculate the saturation pressure. And what the saturation pressure will do is that that will vary, that dew point will vary because it's becoming richer. And that will go down here. And then when that dew point intersects the reservoir pressure here, then it flips from being a gas to being an oil. And that oil composition that it finds below the contact will have a bubble point that decreases with depth. So this would be your GOC, but you know you can, it'll still do the calculations even if it doesn't find a GOC. So I'm not sure what's happening. So this is depth. So this calculation, it calculates the pressure and it calculates all the compositions with variation. Okay? But that's another method you can, because what you could do is that if the sample that you've collected is, say, this is the sample we've collected, and we want a black oil table that goes all the way to saturation pressure at the GOC, then what we could do is that we could use the gradient calculation, and we could take this composition here, the composition at the GOC could be used as our black oil table composition, for example, to create the black oil table for the gas. And maybe for the oil, you'd be using the gas oil contact oil composition. All right. So that's okay. So the black oil table, I think you've got some decent references that are very complete. We've got a general picture of what the black oil tables are, what the properties are, kind of how they're being calculated. The procedure is usually referred to as this Whitson-Torp method. That's SB paper. I don't remember the number, but that's in the for this process of calculating the black oil PVT. It's also covered in chapter 7 in detail in the book. Okay, so that's basically I think treatment for black oil tables.